It's circuit time. So here's a circuit. If you look at this circuit, you are given an EMF of 20 voltage. There is an internal resistor R, and the voltage through the internal resistor is 0.5 volt. Alright, and when you come this side, you got resistor number 9, which is called X. It's unknown, but the voltage across it is 6 volt. There is ammeter 1. We need to calculate the current, of course. And when you come here, you've got resistor 8, which is 2.25 ohms. Resistor 7, which is called Y, which is also unknown. And then we got resistor 6, which is 6 ohm. And we've got a voltage V, which is unknown. And then we got resistor 5, which is 5 ohms. Then we got ammeter A2. You got resistor 4, which is 4 ohms. Resistor 3, which is 2 ohms. And a resistor 1 ohm. Resistor 2 ohm. And then these guys, we can see they are parallel, and then the voltage across the parallel connection is 3 volts. We okay? Am I right now? All right, so we know what we are going to do to master this thing. We are going to apply V, find the voltage, find the current VIR, the resistor, and I'm gonna add, we are also going to find the power, because power is V times I. That is a basic equation. Right, for each resistor, VIRP, and also VIRP, the total ones, then you would have calculated everything. Now, step number 1, like I said, you need to trace the current from the source, from the battery, and see how it's split. And then I said it's best to use colors. We're good, am I right? All right, so we're going to have a current here. I'm going to use red, and when it comes here, it's going to split. I'm going to use green here. Here, I'm going to use orange. And then when it combines back, it's going to be red here. When it comes here, it's split. I'm going to split it into blue and also split it into yellow. When it combines, it is red. Okay, so now let's put those color codes. All right, so here we are. Now, that was step number 1. We trace the current. Isn't it right? All right. Now, step number 2, we can go and apply VIR in each one of them. All right, so let me start here with resistor number 1. Next to number 1, I'm gonna write V equals to I equals to, and then R equals to, well, I know the R is 1 ohm, isn't it? All right, let's wait for the voltage. And then go to resistor number 2, we also write V equals to I equals to R. We know it is going to be 2. Let's do the same thing with all of them here. Now we arrive on this one here. We're also going to write V equals to, of course, this time I know the V here because it's only one resistor, which is 6. And then I equals to R equals to, so I don't know the R. Then we do the internal resistor, so it will be V equals to, well, I know the V, it's 0.5. And then I equals to R equals to, there we go. Then we also need the one that has to do with the total. I'm going to write it right top right corner. So V total, referring to the EMF, so it's gonna be 20. That's a total voltage. And then I total current equals to, and then R total, all the resistance including the internal resistor. Now that's step number 2. Am I right? All right. Now step number 3, you want to make sure in everything that is in parallel, like here the yellow current and the blue for now, the yellow current or this connection must have one resistor. The blue must also have one resistor. It's then you can say their voltage are the same. Am I right? All right. So this voltage here, you cannot say R1 has a voltage of 3. That will be wrong. R2 has a voltage of 3. That will be wrong. You can actually see that line. It encompasses, it includes both. Can you see that? Yeah. Unless it was more like this, referring to one of them. Because that's the mistake most people make. We're good. Even here, when we come here, that V, it's for the 6, but the 6 is the only one there. Therefore, this V will also be for these two after we made them to be 1. Am I right? So that means if I take the Y or R7 and R8 and I combine them when they are together as one thing, this voltage belongs to them as collectively. I think we're good. Are we right now? All right. So now let's go back here. So if we come back here, this is how we're going to do this one here. So you're like, okay, let me combine this, because remember, to do any calculation, you're looking for the VIR, where you know two things. At this point, as far as we have put our data, we only have one thing, one resistor, only resistor, only voltage, only the voltage. Can you see that? We want one of them that has 2. Now we remember, in parallel, each line that is parallel to the other one, in other words, each connection must have one resistor first. We add all in series. So if we add these two together, it's 1 and 2. It's 3, ne? Once they are 3, their voltage will be the one that's given, which is 3. So let's start there. So I'm going to say, working with the yellow here, I don't know, maybe let me use a yellow color so that maybe say we can trace this so that it looks good. All right, so I'm going to say V equals 3 for the yellow combination. We good, right? And then the current, I do not know it. The R must be all the R's on the yellow, which is 1 plus 2, which is 3. We good, am I right? All right. So now to get the current, it will be V divided by the 3. We okay, ne? Everybody knows 3 divided by 3 gives us a 1. So the current will be 1 ampere. You had to put them collectively. Now it's easy for us to know what is the current passing through R1, which is 1 ampere. We good, am I right? Also through R2, it's a yellow current, which is 1 ampere. This one helped me to get the current there. So I might now remove that. I don't need it anymore. So now, if I look at each individual resistor, this one, I can now get the voltage. Am I right? I can also get the voltage, but I must keep in mind, when I add the 2 voltage, they must give me 3. Am I right? All right. So now, since you have I and R, to get voltage, it's I times the R. Am I right now? Yeah, which is going to give us 1, because it's 1 times 1. So we're just getting a 1V. Then we come to this one here again. You got 1 ampere for the current. The resistor is 2. So I times R, 1 times 2, we get a 2. Can you see that? Let's verify the red numbers. This voltage is 1. I add it with that one 2. It's a total of how much? Of 3. Everything is well with that one there. So far so good. Am I right? All right. Now, while we are still here in this connection, we said the 3 volts belongs to the parallel connection, but I must make sure in that parallel connection there is 1 resistor here, 1 resistor here. I don't have anything in series. So to use this 3, I can't use it directly on the 2 alone. No, it will be wrong. I can't use it on a 4 directly. It will be wrong. I need to combine them first to make them 1. Isn't it, gentle people? All right. So again, for this one, because it's blue, let's use the blue equation. So I'm going to write V equals to, so if I'm going to use V as 3 for the blue line, the blue resistors must be added first. We good? All right. Then we got I equals to R equals to, meaning these, everything that is on the blue, which is 2 plus that, plus 4, which is 6. We good? Am I right? To get the current, it's always V. If I've got V, it's always V divided by I, V divided by R. Every time to get one of them. And then to get V, just I times R. So it will be 3 divided by the 6. Am I right? It looks like a half to me. Isn't it right? Yeah, you can verify it with your calculator. So we've got 5 there. I'm sorry, 0.5. So now I can go to each resistor individually and put the current. The current through this one, the blue one, is going to be 0.5 amps. And then the other one here, it's also going to be 0.5 ampere as well. Are we together, gentle people? All right, I believe we are winning. All right, while I'm still at it here, I'm going to calculate the voltage of R3 of the 2 ohm resistor. All I need to do is I times R, meaning 0.5 times 2. It's half of 2, which is actually 1. We good, right? And then this other one, it must be 0.5 times 4, which is half of 4, which is 2. Isn't it right? Let's verify, because we know in the parallel connection, the voltage is 3. So look, we've got 1, the red one, plus 2, the red one. It is still 3. So far, so good. We're happy with that one. Am I right? All right. Now, that was step number 3. Number 1, trace the current and see how it's split. Step number 2, apply VIR in everything. Step number 3, make sure in the parallel connection there is only 1 resistor in each one of them. Am I right, ne? All right. Then the other key is to look at the let me say something. If I'm going to use 1/1 for the parallel, I can only do the 1/1, meaning using the parallel way to calculate. Am I right? I can only do that if in each line, in each branch, there is 1 resistor. To use the parallel way of calculation, first, I must have 1 resistor here. Take care of the series first. So, which means I'm going to have to add these 2 to give me 3. Then I'm going to have to add this one to give me 6. On the blue, there will be 1 resistor. on a yellow, there'll be 1 resistor. Now that's when I can do 1 over 1 over. But you cannot say, take this one and say 1 over 1, 1 over the 2, plus 1 over the 2, plus 1 over... It will be wrong. First, make sure in a parallel connection, there lies 1 resistor in each one of them. There is nothing in series in them. Then it will be absolutely right. I believe we're okay, right? Right. Yeah, that's what I was stressing even with talking about that. All right, so now another thing which is, let's call step number 4. Step number 4, you begin to check what I call the mother parent or the mother voltage, meaning the total current or the total voltage. Am I right? Because it splits, sometimes it combines back. Am I right? The splits combine. Am I right? So here we were splitting the current. Remember the yellow current is what? It's 1 ampere. Am I right? Ne? And then the blue current is 0.5. So that means the reading on ammeter A2, it reads the yellow current, which is 1 ampere. But here, once we're going to the R5, we can see the blue current and the yellow are now joining. They are combining. Isn't it right? So that means red, it's blue plus yellow added together. The yellow is 1 ampere. The blue is 0.5. So let's add 1 plus 0.5 and then we figure out how much is that current. How much is that current? It looks like 1.5 to me. Is that right? Yeah, so the current is now 1.5. So you see, I said in step number 4, you're trying to look at the total current, the combination and the splitting. In other words, where the current combine or where the current splits or where the voltage is being used up, splitted and combined, all those kind of a thing. It's always one of those ones where people get stuck. So now on R5, we are happy we got 1.5. Now we can work out the voltage, isn't it? It's 1.5 times that 5. So let's use our beautiful calculator. 1.5 times 5. What are we getting there? 7.5. So our voltage here is 7.5. We normally call voltage drop. You minus, which means out of the 20, this one is going to use 7.5. Out of the 20, the combination, in parallel, they're going to use 3. Am I right? But the 3, it's counted only once in a parallel. See, we're winning. All right, so now we've got everything here, VIR. Am I right? Ne? So when we come here, the current that we have, it's 1.5. It's going to split into something and split into something. I don't know how it's going to split. I don't have anything like 2 information here, 2 information here. Am I right? All right. So now you know the red current is how much? 1.5. So personally, I will quickly trace in every line that is red. So we know 1.5 is red. So here we are on the red, on the red, on the red. Look, ammeter 1 is on the red, isn't it? So it's reading 1.5. How about resistor 9? It's on a red, ne? Yeah. So now I can put the current here. It's 1.5 ampere because sometimes we forgot that we already got it over here because we're paying attention on this one. Now we forgot this one's already there. So I quickly take off it. So let's look at it again. We go. Look, it's passing through the internal resistor. Can you see that? So the current is 1.5 in the internal resistor. So we can put it there as 1.5 ampere. There we go. And then it gets there. So far I've traced the current. So now you begin to realize resistor number 9, which is called X, which you do not know. You can now calculate it because there are 2 information now. Can you see? So it's going to be 6 divided by 1.5. Let's use our beautiful calculator. 6 divided by 1.5. I'm getting a 4. Are you not getting a 4, gentle people? Yeah, so the resistor, it's 4 ohms. So that means X, it's actually 4 ohms. So we already have three things. So far, so good. And we trace if we can figure out something that has two things there. Here, that means we are calculating the internal resistor. We've got the voltage of 0,5. We've got the current of 1.5. So to get it, it will be 0,5 divided by 1.5. So 0,5 divided by 1,5. What are you getting? 0,33, ne? Which is a third. Am I right? Yeah, I'll write it as 1/3 and then ohms. And now you have arrived. So you have gone all around. Now, I said now, since here we were stuck, we didn't know what to do. So check the total voltage or the total current, how it's splitting or combining. But we figure out here, because we knew the current was 1,5. When it came here, we didn't know how the current was splitting. Am I right? So the current is not helping me by anything. So that means the secret must be maybe on the total voltage. All right, let's trace the total voltage. First, original voltage, how much it was? It was 20. Am I right? Ne? When we come here, it dropped by how much? By 6. Isn't it right? Yeah. It dropped by 6. No. I think we missed a point. I think it's here. It's 20. There is 0,5 here. Can you see? It first dropped by 0,5. So let's use our calculator. It will be 20 minus 0,5. Because this is the only part that remains. Am I right? No. After dropping by 0,5, it also drops by what? By 6. Then minus 6. And then here we do not know it. And then here it drops by 7.5. So minus 7.5. And then here in the parallel it drops by 3. Remember the 3 is counted only once. Yeah. And then what's left? Whatever is left belongs to the remaining resistors, which means it belongs here. That's what I mean. Can you see that? Yeah. But since this is in parallel, that 3 will be for the green current for if there is one resistor there. Am I right? And that 3 will also for the orange here if these two are combined to be 1 first. Am I right? Yeah. So which means now we know the reading here. It's going to be 3. So I can put 3. And then at the bottom, it means it must be 3 when it's like this. It's 3 when they are combined like that. Can you see that? Yeah. All right. So I'm going to leave it for now. Let's do the calculation here first. Because in the 6th one, the green one, we can now work out the what you call here, the current. Am I right? Yeah. So it's going to be what? 3 divided by the 6. Am I right? Ne? 3 divided by 6. What we got? We've got a half. I'm getting a half. Are you not getting a half, you guys? You sure? All right. It's 0,5 ampere. Now it's better because now, remember the red current will come here and split. Am I right? If it was 1,5 here, this one gets a 0,5. The remaining goes there. Can you see that? Yeah, so we can do that. So how much current is remaining? It's 1,5 minus 0,5. How much remains? So we remain with 1. So which means the orange current is 1. So now I can come here to this one, to VIR, and say the current here, it's 1 ampere. Then I can come also to that resistor 8 and say this is 1 watt ampere. Voila! Look at resistor number 8. It now has 2 things. Am I right? Now I can calculate the voltage. It will be 1 times 2,25. Well, anything times 1 remains the same, which means I'm having 2,25 volt. So far, so good. But remember, we knew that the voltage of these two guys combined, it's 3. Isn't it right? So that means out of 3, this one took it's using 2,25. How much remains? 3 minus that number. Okay, how much you getting? Is it a quarter? 0,25, something like that. Oh, 0,75. Oh, okay, 0,75 V, which is 3 over the 4. Am I right? Now we have two things. Can you see now? Yeah. How do we get the R? The voltage divided by something every time. 0,75 divided by 1 is going to be that same number. Am I right? Ne? 0,75 ohms. So now we've got VIR in every resistor. But now let's go for the total. Here's for the total here. The total, remember, it started here from the battery. Am I right? Ne? Now we know we've got the V here by the battery, but there is a current passing through. What color is there? It's a red one, isn't it? Yes. Which is 1,5, correct? Yes. So now we can put the current down there and say the current is 1,5 ampere. So that means now we can get the total resistors, which is 20 divided by 1,5. What are you getting? 13,33333. I'm gonna write. It's 40 over the 3. Am I right? Ne? Yeah. Or if we put it in the decimal, you're getting 13.333, and so on. All right. Now, so far so good. Now I wanna do the last thing. Because we said let's do everything, let's include also the power. So we're going to include the power now. Now, power. Power, we said power is given by VI. Am I right? If I times this power by time, it's now energy, work done. You see how easy it is now? And you see there? So we want V times I. Am I right? Okay, so I'm going to start with this one. This one, I'm going to put it in purple. So power, it's V times I. What is the V there? What is the V there? It's 1. The I, it's also 1. Am I right? So the power will be 1 times 1, which is 1 W, 1 watts. All right, so let's go to the next one. Let's take the power. The power must be V times I, 2 times 1, which is 2. Am I right? Ne? So which is 2 watts. And now we come here on the 2 ohm resistor. We say power equals to V1 times I, which is going to be 0,5. 0,5 watts. And I'm gonna mention something about the bulbs. Okay? Remind me that. All right. Power equals to, again, we're looking at 2 times 0,5, half of that one, half of 2 will be 1 watts. All right, and then, again, let's do power for this one here. I'm going to write it next to it here. I'm going to say power equals to, so we're working at, what is it, 7.5, am I right? Times by 1,5. How much you getting? 11,25, right? 11,25 watts. Okay, let me make space so that I can put a W for the units. Watts, there we go. And then we come to the green one, this one, the 6 here, and we're going to write power equals to, it must be 3 times 0,5, 1.5. It's half of 3. 1.5 watts. And then let's come to this one here. The 7 one, it's 0,75 times 1. Well, it's going to be 0,75. Am I right? So power here, it will be 0,75 watts. And then we come to the 8, and then let's put the power equals to, we're going to take 2,25 times 1. Well, it's going to be 2,25. 2,25 watts. Wow, this is nice calculation. Then we go to resistor number 9, which is X, and then the power it's going to be 6 times 1.5, 6 times 1,5. We're getting 9 watts. We're good, right? All right. So let's check the power on that small resistor, the internal resistor. I'm going to put it right at the corner. Power equals to, it's going to be 0,5, 0,5 times 1,5. How much you getting? 3/4, 0,75. 0,75 watts. Now, we did the powers for all resistors. Can you see that? Now, let's do power total. Power total, meaning we'll be taking the 20 times 1,5. Am I right? 20 times 1.5. What are you getting? Wow, a beautiful number. You're getting 30 watts. We good, ne? All right. Now, let me mention something before we can check all the totals. Now, everything, a bulb, it's a resistor. If they say here we had bulb 1 and bulb 2, you get it, ne? Bulb 3, bulb 4. And then sometimes they ask you which bulb is brighter. The one with bigger power, with a greater power, is the brightest. The dimmer one is the one with less power. Remember, like I said, to get power, we say V times I. So which means the greater the voltage, the greater the power, the greater the current, the greater the power. Am I right? Yeah, there are other formulas you can actually, you don't need them. No need for me to write them here because it looks like there are many. So that's what I wanted to mention, because they'll say between bulb R1 and R2, which one is brighter? Oh, I said the power is 2 here. Oh, so this one is, the 2 is brighter. Can you see that? Yeah. Okay, now listen. Here's one thing, here's what we're going to do. Now, you figure out the voltage total. The voltage total, ne? It's equals to all the voltages from all the resistors. Am I right? You know that because we took here 3, correct? And then here we took what? 7.5, isn't it? Here we took what? 3, isn't it right? One time. Here we took what? 6. And we took what? 0,5. When you add them, they give you the total. We okay with that one? Am I right? Ne? All right. Now, and in current, it's easy because you can see when you add the blue must give me the original one. When I add the green and the orange must give me the original one, the total one. Now I'm going to power. We said power is 30. Power total. So we are going to take the power of each one of them, all the resistors, and then we add them. All right? And see how much we're going to get. Here we've got 1. We good? Plus another 1, which is 3. Plus another 1, which is 4. Plus half. So I've got 4,5. And then plus this power here, which is 11,25. And then plus the power here, which is 1,5. Plus the power here, which is 0,75. Plus the power here, which is 2,25. Plus the power here, which is 9. Plus the power there, which is 0, I believe 75. You press equal sign, you must get a total power. That one we've got theta. Are you getting the same thing? I'm adding a question. Here's the question. The question will be, what will happen if we were to take a wire, if we were to connect a wire from G, you see here G, right? Towards C. So in other words, you're going to put a wire here to C. What will happen? Which path? Or let me tell you exactly what will happen. And then when we ask the questions, now we understand what's going on. All right, so I'm going to use a big, thick line. Let's use pink. All right. Now, first, all right, so let's work with the red first. First, the current starts from here. Am I right, ne? It's going to move towards the right. So current always tries to avoid, to dodge the resistors. Current is like who's that? Our markets, the taxi drivers. They want to dodge the metropolis, ne? Resistors are metropolis. So this is Barra Station, whatever it is. So then the current comes out here. It comes here. The moment it gets here, it says, "Let me go this road." It says, hey, there's traffic here. There's a metropolis, and it says, "I'm gonna take a shortcut." Oh, nothing is here. Good. Then the current will now come this way. This is what we call short circuiting. You will say like shortcut, short circuiting. Am I right? Ne? Then it gets here. It cannot go back this side and then it come back here because it's coming back where it came from. Am I right? So it must now continue to go where forward. Am I right? Ne? Of course, all right, it will be splitted into that and splitted into that yellow. And then it will combine back, and then it's back here. Now, what you notice is that resistor number 9, this resistor X, am I right, ne? Let me circle these guys, and that guy. There's no current flowing any longer. Yeah? You see it, ne? Yeah. So, if they ask me, what will happen to the current in emitter 1? Will it increase, decrease, remain the same, or be zero? This case, it will be zero. There will be nothing. Am I right? Uh-huh. Let's say this resistor X and that resistor and that resistor and that resistor and that resistor. Let's say all of them were bulbs. You know a bulb, ne? Yeah. They'll say, what will happen to this bulb? Or maybe bulb X or bulb this one 6 and so on. What will happen to them? Will they become more brighter or dimmer or they will be off? There will be no current. They will be off. Is it making sense now to you? Yeah. So now you begin to see that what's happening now. Now, let me add another question. Here's another question. Now, if they say, what will happen to the total resistance of a circuit, total, will it remain the same? Will it increase? Will it be zero? First, let's look where the current is flowing now. The current is going through internal resistor, correct? Yeah. 1. It's going to go through these guys in parallel. Am I right, ne? It's no longer going through this. This one is bye-bye. This one is bye-bye. So this one is bye-bye. So we have removed the resistors, but still there are some remaining. So what happened? There is total resistor become what? Less. Total resistor become what? Now, wait a minute. Here's V equals to I or. So if total resistor becomes less, can you see that? Can you see that? Because resistance is directly proportional, or voltage is directly proportional to the resistor. The lesser resistance, the lesser the voltage. You get what I'm saying? Yeah, exactly. Or resistor is inversely proportional to the current. The lesser the resistance, the current, it will increase. Then they will ask a question, what will happen to the current? You see, will it increase or what? It will increase, ne? Yeah, there we go. You see, I'm giving you those funny questions they love to do. So what I did here, by drawing this thing that I'm calling short circuiting, it is another way if they were to say to you, what will happen to the circuit if resistor X, this one was removed, and 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 this one was removed. You know, they love to ask something like that. Am I right? Yeah. Then everything becomes so clear. Now, what if they were to ask me about the power? Because you figure out that V equals to IR, so you know the resistor went down, and then the I went up. So in other words, if V is constant, the I will go up. Am I right? We just compare two things every time, ne? Yeah. So okay, let's do this thing. If the resistor went down, then if I'm comparing resistor and I, that means the voltage, I'm making it constant at this moment. Am I right, ne? Yeah. Then you say, oh, the current therefore must increase, provided the voltage remain constant. But if I'm comparing R and V, I'll say, okay, V will also decrease if I is what? Constant. Yeah, I should have mentioned that one. All right, we good, am I right? Yeah. But if this is for the total, the EMF would not have changed the EMF. Am I right, ne? Because it's still 20. Am I right, ne? So that means the question here will be, what happens to the current? The current will increase. Wait a minute. The current goes up. Then they ask me, what happened to the total power? Remember, the V is constant. Current went up, which means the power also goes up. And then they'll say, what happened to these bulbs? They are getting more power. They will become more brighter. Am I right? Well, you know it. Think about it. If you connect 20 bulbs and then it's okay, it's bright. Then you remove 10. You are left with less, with 5. The 5 becomes more brighter because they're getting more energy, more power. Isn't it making sense? Yeah. That is perfection. This was a wonderful, wonderful, wonderful question. I never thought I will even get to that point. So once they give us the time, they say through resistor 1, the current that's flowing there, it's passing there in 3 seconds. 3 seconds. 3 seconds. Meaning delta time equals to 3. And then they say, what is the energy, which is work? So work equals to power times delta time. Am I right, ne? Because we're focusing on resistor 1. Am I right, ne? So I want the power of it. What was it? It was 1. Am I right? So it will be 1 times 3 seconds. Then I get my answer as 3 joules. We good, ne? All right. Now, they can give you time for each one of them. We good, right? Now, let's say now they ask me, how much charges? Remember, I gave you, there was 3 equations. Let me just write them again for you. I said the one equation is V equals to IR. Another equation is power equals to IV. And then the other one, I call it quit. It's Q. It's almost like you're writing quit. I'm quitting the school. But you're not putting the U there. And then you're just putting I and then delta time. Can you see that? The Q is for the charge. And then they say, hey, how much charges is passing through here? All you need is say, what is the current through this one? It's 1, isn't it right? The current will be 1. And you say, what is the time? The time they gave me, it was 3 seconds. So it will be 3. So what's passing? It will be 3 coulombs. 3 what? Yeah, let me add it and add a little bit of electrostatic. According to electrostatic, this is what you know. 1 electron, it's a charge, am I right? 1 electron equals to 1,6 multiplied by 10 to the negative 19. You can say coulomb. It also applies also with the joules. Now I'm going to say coulomb. There we go. And then now, this is one charge. If I wanted to figure out how many electrons were passing there, so which means I'm going to take my charge divided by 1,6 multiplied by 10 to the negative 19. This will give me the number of electrons or protons. That's why this number can be written as minus for the electron. Keep it as positive for the proton. You see, I just added extra masala. You got it, ne? So what you need, you guys, it's 1, 2, 3 equations. So now, these 3 will work all the time. I know. Sometimes you guys, they give you this equation of EMF. They say, okay, EMF, oh, I'm going thick there, yeah. So you're going EMF equals to I total, open bracket, you're taking total resistance of the external, which means this is total resistor without the internal resistor, and then plus internal resistor. Actually, this is like total resistance. Can you see that? And then the EMF is like total voltage. You don't need it, because here it's measured in voltage. It's actually V total. Here you've got current total. This is total resistance. Again, you're coming back to VIR, but you didn't realize that. We okay? And then coming back to this power one. The power, like I told you, power equals to VI. And then you need that. You need V equals to IR. Now, sometimes this power, they say, no, wait a minute. You said V, it's IR. Can't I put IR in place of the V? Oh, yeah, you can. So it will be IR times another I. There are 2 I's, can you see? So you're having I squared times R. So this is another form of equation of power. You don't actually need it. You can always come back to this one. All right? All right. And then sometimes you like, from here there's an I. I know from here, from V equals to IR, I know that I is given by V over R. So can't I write power as V? In place of I, put V over the R. Then the equation becomes V squared over R. Then you find them giving you this formula, that formula, and that one for power. They're like, yeah. But I told you that work equals to power multiplied by time. Am I right, ne? Of course, you know power, it's VI times delta T. That's the one we're using. Can you see that? Now, because they realize there is a VI for the power, they'll say, work can also be, they now use this one for the power. They write it as I squared R times delta T. You're like, work, it also has many equations. And then they use this one again, V squared over R times delta T. You're like, wow, physics, there's thousands equations. No, you just have 3. You see, I taught you how to do it, V total. I never said there is a EMF, I'm going to use the EMF equation. No, every time VIR. I think this one concludes the deal. How was that? That was cool, ne?